Let us now study potential energy of a magnet in a uniform magnetic field. Okay, so first let's take a magnet here. This is the north pole and this is the south pole of a magnet. It's kept in a uniform magnetic field, so the lines are parallel to each other. Okay, now first let's see what will be the torque there. Okay, we already derived an equation for torque. Okay, the magnitude of torque, that means we take this way, that's equal to magnitude of the dipole moment into the magnitude of the magnetic field into sine theta. Okay, so this we know. If you take magnitude, if you write simply, torque tau is equal to Pm into B sine theta. This derivation we already learned. Okay, now what we do now, we have to see that suppose you move this magnet, okay, in this direction, in the opposite direction this way, through very small angle d theta. Okay, so if the magnet is moved through d theta, okay, through d theta, okay, that means a small work is done. Okay, a small work that is dw is done. Okay, so you move it slightly only, so small work is done, that is dw. Let's see what's the value of the work done. Okay, so in this case dw is equal to torque. Okay, that is tau. I'll take another chalk here. The torque, the external torque, this one, okay, into, or you can take a magnitude also, okay, into d theta. Okay, so now we know the torque here. This torque, external torque we got, that is Pm into B into sine theta into d theta. This is for the small work done. Okay, small angle we have changed. But now imagine that if you are turning much more bigger angle, you're doing a lot of work now. So for that we have to integrate this. So the total work done, okay, is equal to integration of dw. So when we integrate this, we'll integrate right side also. So Pm B sine theta sine theta d theta. Okay, so what happens now? You can take the constant terms outside. That is dipole moment Pm is constant, magnetic field is constant. So take it out. So Pm into B into integration of sine theta d theta. Limits we must write now. Okay, so limits, you see, lower limit we write as theta dash. Okay, that is the initial. Final limit is theta. So here also lower limit is theta dash. Final limit is theta. Okay, integration of sine theta is what? It's minus cos theta. So we have here minus Pm. I'll write the minus outside. Minus PMB into cos theta. Okay, lower limit is theta dash, upper limit is theta. Okay, so remember minus I written front here. Okay, now so we get here minus PMB into upper limit is so cos theta. Instead of theta you substitute this theta, minus lower limit is cos theta dash. Okay, so we got this term now. So this is the work done. But if you see, okay, I'll write this equation a little bit on top. Rub all this. Okay, so in this equation, we'll take this equation. Okay, if theta dash is equal to 90 degrees, what will happen? Okay, so if theta dash is equal to 90 degrees, let's imagine the initial condition, it was at 90 degrees. Okay, so this part cos 90 is how much? It is 0. So this term will vanish away. So we'll get work done is equal to minus Pm B into cos theta. Okay, this term we will get now. So that's the work done. Then this work now we can also say it as, it's stored as the potential energy. Okay, work is stored as a potential energy here. So we can write here U is equal to minus Pm B into cos theta. Okay, this time we'll get here. We'll take another chalk here. Now, so this is the work done. So we know that A vector dot B vector is equal to AB cos theta. I'll write here A vector dot B vector is equal to AB cos theta. So this formula I'm going to use here. So what we get is U is equal to minus of Pm vector dot B vector. So it becomes a dot product. So you can use this formula sometimes in some set, or else you can use this vector form here. Okay, so two ways we can write. Next is we'll see the special case here. Case 1. Okay. So first case is if theta is equal to, in this case theta, okay, this formula I'm going to use here, theta is equal to 0 degrees. Then what will happen? Okay. Then what happens here in this equation? Let here potential energy is equal to minus of Pm Be to cos 0. What's the value of cos 0? Cos 0 value is 1. Okay. Cos 0 is equal to 1. Know that. So this term becomes u is equal to minus Pm into B. Okay. So this is one special case here. Okay. Next what we do, we'll go to second special case here. We'll rub this term. Okay. So case 2. Second case is if theta is equal to 180 degrees. Okay, what will happen then? Okay, so potential energy is equal to minus Pm into B into cos of this angle. Theta will become 180. Cos 180. What's the value of cos 180? It is minus 1. Okay, cos 180 is equal to minus 1. Okay. So what happens now is you will get here potential energy U is equal to minus into minus will become plus. Okay, so plus we can leave it also. Okay, plus Pm into B. Okay, and then cos 180 is minus 1. So we get this as maximum value here. Okay. That means what? Theta is 180 means it is opposite here. Okay, so remember this is the north pole this side and this is the south pole. So at you say anti-parallel, the magnet is anti-parallel means we get the maximum potential energy. Suppose it's parallel, then theta was 0 degrees. We saw first case now. Then we'll have minimum potential energy. Okay, so this is about the potential energy of a magnet in a uniform magnetic field. Okay, so kindly go through the equations here. It's a very simple thing only. Okay, go step by step and note down this. Okay, so thank you for watching.